Okay, so, well, first of all, I want to join the other speakers and thanking the organizers for the invitation to be here. It's a great conference, and it's always great to be here back in Santa Barbara. I'm going to talk about twist bilayer graphene also, and well, the most important part of the talk is my collaborators. Anusri Ndata, so she was a postdoc in Madrid and she's now in Paris. Maria Jose Calderón, also from my institution, and Alberto Camjayi from Universidad de Buenos Aires. Well, I think we are all relatively familiar with twist bilayer graphene. Essentially, some aspects are these very flat bands, the fact that we have this very large unit cell, and the possibility that it can be doped up to more than -4 electrons per unit cell and plus 4 electrons per unit cell, some more, and that it's doped with a gate. There are many, as we have seen also in some previous talks, there are many different correlated states that have been observed with doping, superconductivity, ferromagnetism, intervalley coherence, and so on, some of them insulated. What I'm going to focus on is the phenomena that has been called the cascades. In particular, one of the key features are the spectral weight reorganization that is found. So if we don't have a correlated system, what we expect is that as we when we look at the density of states, that it's going to be independent on the doping. It's going to just be shifted. Something that it was already seen quite a few years ago. In fact, these are Esteban's picture measurements, is that, well, the density of states depends strongly on doping. So here you have doping, the density of states when the flat bands are completely filled, it's doped here, and here it is when the flat bands are, so when the chemical potential is here at the flat bands, and you can see that it has, so these peaks have separated very strongly. So in fact, this happens in a very large energy scale of the order of some tens of milli-electron volts. It was later known that this reorganization of the spectral weight happens in what it has been called the cascades. So you can see this is a color plot of this density of states when it's measured here at the center of the Brillouin zone, what is called the AA region. And what you can see, and so in this color plot here, it's shown the doping exchange, and here is the energy, and so it's measured with respect to the chemical potential. And what you can see is that, the density of states is the color, and you can see that, well, so there are, at the integer fillings, there are asymmetric resets, and density of states that, or spectral weight that flows towards the chemical potential, since this very large energy of order of several tens of milli-electron volts. You can see that there are cascades at both positive and negative energies, and they are somehow look like a bit shifted in doping, and that there is here a different shape of the at the charge neutrality point. When one looks at the chemical potential as a function of doping, one can see that there are minima in the density of states at these integer values. And another feature can be better seen when one looks at the different point in the Brillouin zone. This Brillouin zone is very large, so with the SPM you can select different regions. So when you look at this AA region and you have this picture, you mostly see to these really flat band parts. And when you look at this AB region, which is more at the border of the Brillouin zone, what you see more is this remote band. And what you see are these oscillations in the energy of the remote bands with respect to the chemical potential. It was interpreted in terms of the oscillation of the chemical potential. Concomitantly to these signatures of the spectral weight reorganization in cascades, it was observed that the compressibility also have this strong feature, these cascade features, And in particular, what it was pointed out is how there are these peaks at the integer field. These peaks, which are kind of sawtooth peaks, very asymmetric, at all the fillings except at the chemical, but at the charge neutrality point, in which it's symmetric. And there are also regions of negative compressibility. There have been different ways to discuss these cascades, but in one way or another, so they introduce the symmetry break. However, some aspect of the cascade is that they are very resilient with temperature. You can see these are in fact Andreas experiments that these signatures in the compressibility remain to several tenths of Kelvin. And in the STM, you can also see that these also remain up to several tenths of Kelvin. On the other hand, and in fact this has been mentioned by Esteban before, when you look at the symmetry, the features that really show the symmetry breaking, these are restricted to low temperatures, only of a few Kelvin. You can see here, for example, is the temperature associated to the ferromagnetism close to nu=1, so of the order of 7 Kelvin. And here, for example, you can see how the insulating state at nu=2 is restricted to also a small region of temperature, but there are signatures of resistive states at different, at higher temperatures. We know that correlations show up not only in symmetry breaking states, but also they can be associated to even the normal state, the non-ordered state, for example, due to the formation of magnetic moment, which really, or sometimes the localization of the charge, that really create a very strong reorganization of the spectral weight, as yesterday Laura Fanfarillo, for example, was discussing. So, oops, this has become crazy. Okay. So the main message of this talk is that what we propose is that the cascades are not a consequence of a symmetry breaking process, but they are a property of the normal state of twist bilayer graphene, which are, and so they are present really in the normal states, and they are a consequence of the local physics associated to the formation of magnetic moments and the tendency to form heavy quasiparticles. So I'm not saying that there is no symmetry breaking in twist bilayer graphene. Of course, we know that there are states with symmetry breaking, but what we are saying is that these states are only happening at low temperatures of the order of a few millicale, and they happen in this already distorted state of the cascade. So they are going to inherit a lot of the spectrum. Okay, so the way in which we are going to introduce this, what we are going to study, so we are using an 8-orbital model per valley. So we have in total 16 orbitals for magic angle graphene. So this, what we are doing is we are adapting the magnetization that it was proposed by Karl, Katsiras, Viswanath, and colleagues. So in this model, what we have in each of the valleys, so these orbitals are placed at the three lattices that can be defined on the twist graphene bilayer. So there is a triangular lattice, there is a honeycomb, and there is a Kagome lattice. And so, well, this is the flat bands that we are considering. So the results that I'm going to discuss have been published recently, but in the paper, so we were using a dielectric constant of 12. Now the results I'm going to present here use a dielectric constant of 20 that I think are a bit closer to the ones in the experiment. But essentially the discussion is the same one, and whenever it's not, I will mention it. So, well, as you can imagine, with so many orbitals, we have a lot of different interactions. If we want to pick up the physics of the local formation and this reorganization of the density of states, we need techniques like dynamical mean field theory. And of course, we are not going to be able to deal with all the interactions that are in our 16 orbital systems with that. In fact, there are some of the interactions are even not local. So somehow, these are the interactions that you can see here. They even follow. This is the distance between the orbitals. And you can see there are many. And among different orbitals, intra-orbital, interorbital, on-site, inter-site. Now, what we saw a few years ago is that is that not all the orbitals are equally important. This was has been already predicted proposed by Christian Howlett, and in which somehow there are 2 of these orbitals per valley, so in total 4, that are playing a very special role, in which they are giving most part, so they are at the center of the Moiré unit cell, they form a triangular lattice, and so most part of the flat bands are given by these 2 orbitals, except at gamma. So you see that these are much flat, and so even also the interactions that involve these orbitals are the largest ones. So when we calculated these interactions, what we saw is that, well, contrary to what Christian had done, is that the interactions with the other orbitals involving the other orbitals are not small. So they have to be included in the model. However, we confirmed that only these orbitals are expected to give rise to local moments. So then what one can do is one can treat this twist by Lie graphene separating 2 kinds of orbitals. So there are some orbitals that are going to be very strongly correlated and that account for most part of the flat bands here except at gamma. This is what it has been correlated in twist by Lie graphene to the so-called fragile topology, and some other orbitals which are coupled to these flat orbitals through hybridization and through interactions, and they are also interacting among them. So we are going to separate very strongly correlated orbitals and less strongly correlated orbitals, but all interacting. So this is a kind of extended heavy fermion-like model. And so, because only these orbitals are expected to give real magnetic moment, so what we are going to do is also we are going to separate the interactions. In particular, so we are going to treat this the interaction which is on-site, which is among these very strongly correlated orbitals, both the intra and inter between these AAP orbitals. I'm calling AAP to this strong correlated one. With dynamical mean field theory. The other ones we are treated at the Hartree level, and we are doing a double self-consistency loop inside this, let's say, the dynamical mean field theory self-consistent, and then with the Hartree. Well, we are using for the impurity solver of the dynamical mean field theory, the CTQM. We are going to work at 6 Kelvin, if I don't say any other thing, and with this dielectric constant. There are small Hund and exchange terms that we are neglecting because what we want to study is the normal state, not the symmetry breakings. And so for these terms are not given importance because they are small. So, and the fact that I'm going to focus in the normal states, I'm going to impose that we are in the normal state, okay? So then it's, we know that everything that we get is really not a consequence of a symmetry break. Okay, so let me first look at what we obtain with the spectral weight reorganization, how it compares with experiments. And so you can see here the results. You see that we reproduce this, the strong reorganization of the spectral weight. This happens up to energies of the order of this on-site interaction that for these values is of the order of 26 milli-electron volts. In fact, these spectral weights that you see here are the Hubbard bands of the system. So you see how the spectral weight flows towards the chemical potential in the form of cascades of positive and negative energy. we find the resets, these asymmetric resets in the density of states, and also we have this different shape at the chemical potential. And also here the oscillations of the remote bands. Something important is that in our calculation we are having the total density of states, both the one that you will observe at the AA point and the one that you will observe at the AB point. You see here when we look at the density of states at the Fermi level, you also find these minima at the integer fillings. Somehow the interaction, so the density of states vanishes, but in a kind of pseudo gap-like feature. Is not a hard gap. And also in the compressibility, we find these sawtooth asymmetric peaks at the integer fillings, except at the charge neutrality point, which is symmetric. We also find regions of the negative compressibility. Some of you that probably knew this, that have read the work before, and before we were in the published work, we didn't have this negative compressibility. We have it now. So this is not associated to the change on the parameters. This is associated to a change, to a new different criteria for the definition of the chemical potential. So essentially, so here we are having these regions with negative compressibility, but there is no new physics. So the physics are these resets that we are finding in the system. So now you can see now where this is coming from. If we go back to our electrons that we had, so what we find here is that when we are doping the system, so you find here that, well, we are filling these strongly correlated orbitals, and you can here see that there are some kind of steps. And what is interesting is that due to the interaction to these very strongly correlated orbitals, these other less correlated orbitals, the filling is non-monotonous. So it's increasing and decreasing. Now, of course, these features that are observed in the density of states are going to have consequence in the spectral weight of the bands. And in particular, you can see how these bands have let's say, the spectral weight, for example, of the flat band changes. This is at the charge neutrality point. This was the shape in the non-interacting case. You can see here, this is very flat here, and this is just a few milli-electron volts. You can see how the spectral weight has reorganized completely and has gone to the here to these Hubbard bands. Interestingly, you see that the way in which the organization happens is different at gamma, where we have these less correlated orbitals, and at the other part of the Brillouin. So what we expect, that we would like that it's found in experiments in ARPES or maybe with the QTM, is some selective, some momentum selective incoherence. Now you can see now how this is doped. When the system is doped, how the bands change. You see that, so how this band, the Hubbard bands are kind of shifted here, and so towards the formation of what it's a kind of heavy quasi-particle that at this temperature is not completely formed. And then you also see that when we approach the integer, so then there is a kind of band flattening. You see how there is this bending that has been discussed previously at the Hartree level, but then there is a kind of recovery close to, partial at least, to the integer filling. Okay, so this was the main thing I wanted to say. So what we have done is with this TMFT plus Hartree calculations, we have this kind of extended heavy fermion-like model, and that it's showing these cascades in the density of states that compares well with the experiments in STM and also in the compressibility. And what we say is that this strong reorganization is due to the formation of local moments, not to a symmetry breaking process. And so this is the state in which later the ferromagnetism or the intervallic coherence will appear. Well, we expect this very strong momentum and doping dependent incoherence that we expect that it can be observed in future experiments. And what is very important is that this brings us in connection, this brings twist bilayer graphene in connection with the other strongly correlated system, such as the cuprates, the pnictides, and the heavy fermions, where we know that this incoherence is very important. So Esteban was saying that at the beginning we are trying to compare this with the cuprates. It's more in connection with heavy fermion, but essentially this incoherence is important. So just some things I didn't have time to discuss. The temperature dependence. We have some results in the paper. Essentially, this is quite resilient with temperature, but it's going to be broadened because the moments are kind of resilient, but the quasiparticle is not. Well, this is still very preliminary results, but you can see that, well, the cascades are going to show up also in transport, in particular, so they are behind the, so we expect to have these resistive states that are also, have also been seen in experiments. We do expect to have similar physics in twist trilayer graphene, where in fact the cascades have been observed experimentally, and a heavy fermion-like model has been also proposed by, in fact, by Shankar and collaborators. And well, so yesterday it appeared a paper that confirmed our results, our picture, and they are doing similar calculations, but for a slightly different model. So neither the interactions, not the start point is exact, and they reproduce our cascades, our spectral wave reorganization, and then they look also at an order phase, and they find it's only below 10 Kelvin. Thank you.
Yes, thank you. I apologize. I missed all of your work, although Maria Jose is your co-author. I don't know how that happened. So my question may be very naive. You answered actually half of the question. You are thinking about going to trilayer, which I think will be very nice to extend your work. For the first part, did you look at the Kondo lattice physics at all? I mean, if you did, maybe I missed in your talk.
So what
like
we are
I
doing,
did with Yanzi.
okay, what we are doing is numerics. Somehow is that in Kondo, I will expect to have real steps. Okay, let's say. So somehow you expect that the strongly correlated orbitals are just have feeling that is does not change when you change doping for a while and then a very strong step. We find very weak steps. Okay. In fact, even for the calculation, when we look
in your numerics, you find very weak steps.
Yeah, even in the paper we did. So here we have this value of U of the order of 27 millielectron volts. In the paper, it was 45. So it was higher. Still, the steps are weak. So somehow it's really I think we are not in the Kondo limit. It's more like going there. And also is that the tendency to the quasiparticle. What we find is that somehow it's better formed when you go to very low temperature. So
it's a quantitative issue that one may have to go to very low temperature because U is 26 versus 45.
Yeah,
is what you're saying,
so
right?
maybe it's what I say. So at very low temperatures, this is better at the chemical potential, but we don't find something like a picoid there, but more. It's more, I think, it's mixed valence.
I'll look at your paper.
Yeah,
I got it.
Yeah.
Yeah. So how much of this high temperature cascade physics depends on the details of twisted bilayer graphene, and how much would you expect to be generic to any graphene type system with similar amount of symmetry?
Okay, so this, I expect this for twist bilayer, something similar for twist trilayer. In the ABC on boron nitride, we did the previous work. And for example, what you expect for we studied the trivial band. And there, what you expect is more like going to a most insulating state. I think the insulating state.
What about if there's no moire at all?
If there is no moire at all, what you observe is just the low temperature state. But let's say what I expect is that what you find without the moire is, I think this is ferromagnetism or intervalley or whatever. When you put the moire, I think that the insulating states that you are finding really have this type of physics, and that if you go up in temperature above, when you can really determine that you have ferromagnetism, you will find effect associated to this incoherent. It's where it's better observed. It's you have it also there in the ferromagnetic state, but you find them better in the normal state.
But the statement is that in the normal state, without a moire, you would not have this type
Without
of physics?
moire, no.
Okay, it
This
looks
is
like you do,
associated-
for what it's worth. Like phenomenologically, it looks actually the same, even without a moire. So
No, you find the insulating states with the moire in the ABC trilayer.
no, I mean at high temperature, there's a large regime where you have compressibility oscillations that are similar, but no anomalous Hall, for example. It's just an experimental observation.
But up to which temperature?
Like 50 Kelvin.
Okay, okay, so I will see that. And you don't have any alignment at all?
Maybe to continue with the same question. As you well know, for untwisted materials, there is also cascade, and this cascade is normally associated with, as I said, with the set of long-range orders, right? So question about basically proving, disproving. If you compare the cascades that you get from potential cascade from long-range orders, do you see any qualitative difference in how inverse compressibility behave?
We haven't looked at long-range order. We haven't looked at long-range order, so I can. So in principle, for example, for the not for the compressibility, but for the density of states, that's very similar in the normal and in the and in the ordered state. There are fine structure in the ordered state that has appeared in this paper yesterday. But we are focused on the normal state.
Right, yeah. But it would be good to see, is there any qualitative difference and to nail down?
Yeah, so somehow what happens is that it seems that, that the ordered state also changes with doping. So at nu equal 1, it's different to some extent.
Right. You need cascade of different orders,
yeah.
Yes.
So, quick question about did you try to investigate like a twist angle dependence? Meaning, we know that we see cascade physics in a certain range of angles, which is like 0.8 to like 1.2 or 1.25. Is that something? What would be the range of parameters of like U and epsilon where you?
Yeah, we still haven't looked at that. So somehow these are very heavy calculations that you cannot do too many. Somehow you expect that in a range of angles you will have this, as far as the width of these flat band are not too large as compared to the value of U. U is what I say. U is around 27 for epsilon equal 20. But I cannot tell you exactly the values. But we expect that in some range this will happen. Yeah.
Any other questions? All right. So thanks again, Elena, for a very nice talk. So officially, there's still discussion time now. If anybody wants to raise any generic questions that came up during the morning session. Yes.
Maybe this is a question which is due to my full ignorance about this story, but I see that you keep discussing this negative compressibility, these compressibility oscillations and so on. So I really wonder how this should be intended, in the sense that a negative compressibility system is, of course, thermodynamically unstable. So you expect that the lattice compensate for that, or there
The,
is some...
the gate. So here this is
So, but the
associated
gate
to the
is-
fact that we are doping with a gate.
But the gate is close enough to screen the Coulomb repulsion, for instance.
So somehow,
that...
so the way in which we understand, in fact, we have now changed the way in which we are doing the chemical potential. So these changes we have these resets, okay? So the way in which now we understand this is, so normally when you do the calculation and you introduce some double counting correction, so this double counting depends on the doping, and so when you have your chemical potential, somehow you have compensated all that. So when you do this calculation, because you are doping with a gate, you fix the double counting correction. And so somehow later you have to subtract some double counting correction. So the way, and this I haven't said here, the way in which we are now defining the chemical potential is just from the band. Okay, I think I probably have taken this out.
So, meanwhile, I can keep asking questions. Maybe wouldn't you also expect some electronic reconstruction for in some kind of frustrated phase separation sense, like some charge density wave due to Coulomb repulsion, which at least on short distances should be present, although there is a screening
I think
gate.
that the tendency, so here there are, so what we are observing here, they are kind of Lipschitz transitions. So they are kind of reset. You really have you have a change in your system. But what I mean is that somehow what I want to say is that the fact that when I say that there is no new physics, I refer to no different physics in what we have now and that what we have a few months ago, because the data is the same one. It's just the way that we are defining that in a different way. So what the physics that we have here is there are all these changes in the bands and in the density of states. So we have this when we are going through all these changes here. So you do have a system, you do have, I don't know how to call it instability, but you have a real reset. I call them resets. Normally they were called transition, I call them resets. I cannot tell you, but it's, well, it's a Lipschitz transition for sure, yeah.
So maybe that's something to follow up on one-on-one discussions.
Okay.
All right. Any other general questions or points to discuss? Seems people are ready for the lunch break. So thanks again to all the speakers this morning. Thank you very much.